Good morning, and this presentation is about the work related to link the Internet of Things and the body area networks. My name is Emil Novakov, and I'm working in the Institute of Microelectronics, Electromagnetism, and Photonics, which is a research lab belonging to the University of Grenoble. How to move? Okay. So that's the research center. We are part of the biggest European research center in the field of the microelectronics. And in my research lab, we design radio frequency communications integrated circuits. And me, I'm managing the research related to the system of radio communications and the cellular radio communications. So the objective of this work is to study the possibility to use the narrowband IoT technology, which is part of the 5G, part of the 4G cellular communication systems, and to transfer data from the body area networks to the central processing unit, which is mostly a server somewhere in the cloud now. So we will try to evaluate the power consumption and the energy consumption of the NB-IoT modem in the real condition. That means with a real network and with real data. And we will test some of the power optimization modes, which are the extended discontinuous transmission, power sending mode, and release assistance. This work is part of the European project, which is named on the slide. So the main idea is to collect information of the human body and to transfer this information to a central processing unit. Most of us, we have now what we call the smartwatches, and in these smartwatches we have at least two transducers who can monitor the heart rate and the oxygen saturation of the blood, and these two parameters can be continuously monitored, and the data should be transferred to the network for processing. There are two ways to do that. The first one is to use the cellular network. So that means that today my watch transfer the information to my mobile phone, and mobile phone transfer the information to the server. So the power consumption, the problem of the power consumption, it's at the level of the mobile phone. Another possibility is to transfer directly the information with a modem which is integrated inside the watch. Today, it's difficult to be realized because of the power consumption of the 4 or 5G modem. There is a special standard in the cellular network standards which are dedicated just to transfer a small amount of data. The first one, the first standard who can transfer really data to the internetwork is the GPRS, which is a part of the what is called 2.5G networks. And today we have three different standards: the NB-IoT, Narrowband IoT, LTE-M, and AC-GSM, which are dedicated to transfer small amount of data through the 4 and 5G networks. So the LTE-M is mostly designed for automotive application, and the AC-GSM is an extension of the 2G network, but for the moment there are no hardware which implement this standard. So for this reason, we try to use the NB-IoT to test the possibility to realize that. There is another possibility, of course, is to transfer the data from the watch or from the body area network with a specific radio access system, which can be the Wi-Fi, Bluetooth, or other proprietary systems, and from the access point to transfer the data to the internet. Of course, the best solution is to have a direct link from the body area network and the cellular network. Here is the different available standards which can be used for this approach. There are some proprietary standards like the LoRa, weightless, RPMA, ZigBee, and some universal standards, which are the NB-IoT, LTM, and so on. Of course, from a general point of view, it's much better to use a worldwide standard like the NB-IoT. What can we do with this standard? We can see a comparative table. The NB-IoT can transfer data rate from 65 to 25 kilobit per second. So the first one is the uplink, and the second one is downlink. The power can be from 23 to 40 dBm. 23, it's 250 watts, which is a relatively small amount of power. The bandwidth is 180 kilohertz, and the modulation can change depending on the propagation conditions. Here are the most important parameters of the NB-IoT system. For our application, what is important that there are some special modes who can configure the link with the network, and these modes can optimize the power consumption. And the goal of this work is to measure exactly what is the power consumption when we are using these optimized modes. To do that, we designed a special system to measure the power consumption of the transmitter, the NB-IoT modem, in function of the different states. So we can measure the voltage, we can measure the current, which is drained by the circuit, and at the same time, we can monitor the radio frequency transmission. We should know that the most important part of the energy is consumed when we are in transmit mode, so when we transmit radio frequency signals. One interesting thing is that the drained current from the device can change from some microamperes to roughly 200 milliamperes. So that's a range of around 1 million. To digitize data with so big range, we are using a logarithmic amplifier to decrease the dynamic range. And all the data are stored in a data acquisition unit, and the data acquisition unit compute the energy consumed for every mode and at every moment of the transmission. So we can see on the left a spectrum analyzer who monitor the transmission of the radio frequency signals. On the right, a simple scope, and here is the system. The NB-IoT transceiver is the small white model on the board. The measurements were done on the real network, one NCE in Munich, in Germany. It belongs to Deutsche Telekom network operator. The model is a Sera N211, and to control the model, there is a special language. It's a very simple language. It's called the AT commands. So the idea is to send a block of data to a server, echo server, and the receiver will send back the data to the model. So we have a round trip. We can measure the round trip delay. I can measure the power consumption in every mode. In the first mode, we transmit information. So the most of the power consumption is done by the transmitter. And in the second mode, we receive information. So we can control the power consumption, the energy consumption of the receiver. So we tested the different modes of configuration. They are explained here, but I will show you directly the measurement results. So on the top, we can see the power consumption of the model, so the current. The big peaks indicate that the model is in transmit mode. We can see that on the bottom with the spectrum analyzer when the model transmits. So the information, the block of information, 128 bytes, is transmitted. And after that, the model switches in receive mode and waits for an acknowledgement from the network. When the acknowledgement arrives, that's somewhere at the end of the period, the model sends a request to release the link, and the link is canceled. And after that, we move in low power consumption mode. During all this period, we drain around 1 milliwatt hour or 1000 microwatt hours of energy. In the discontinuous reception mode, you see that during the wait for acknowledgement. The receiver is switched on. So there is a power consumption, but the receiver waits for an acknowledgement. So the idea is to switch off the receiver and from time to time to switch on the receiver and to synchronize the acknowledgement with this time. So the acknowledgement will arrive somewhere when the receiver is switched on. The network knows when the receiver will be switched on, and he will send the acknowledgement during this period of time. So that's decreased the power consumption of the receiver, and we move to 315 microwatt hours. So 1/3 less energy. And in the last mode, which is the most powerful mode, is the release assistance. The release assistance, the receiver is switched off continuously. And after some relatively long time, when we are sure that the acknowledgement is ready, the receiver is switched on and waits for an acknowledgement. The problem here is that we don't know exactly when the acknowledgement will arrive. So we should wait a time which is higher than the answer time of the network. So this mode is very efficient from energy point of view, but it's relatively slow to receive the acknowledgement and to completely cancel the link. But what we win in this case is that the power consumption is only 100 microwatt hours, so 10 times less than in the standard mode. So with this different mode, it's possible in a very flexible way to tune the system transmitter network in order to optimize the power consumption. Of course, if we want to optimize the power consumption, we pay with more time. We have to wait for the receiving of the acknowledgement. So some results here. And what is most important, it's in blue. So in the standard mode, we have 1,000 microwatt hours. In the discontinuous reception, 330 roughly, and in the release assistant, only 100 milliwatt. So that means that with a simple AA battery, we can transmit 10 packets of 128 bytes, so around 10 kilobytes per day. And the life duration of the battery will be around 10 years. That means that this system now, it's a very, very power efficient and can be really used for application to transmit low quantity of data with a very, very low power consumption. And so that's the result of our work. Today, what we are working is to build a real test system. So not exactly in a watch, but in a small box, which can be related to this body area network and to test that in the real conditions. Thank you for your attention. That's the city of Grenoble, and we can see Mont Blanc, the picture. Okay.
Thank you. Questions? So you mentioned that this project is supported by European funding,
Yeah.
but also with companies involved in partnership.
Yes, we have some companies, telecom operator Deutsche Telekom, because they are interested by this kind of system, because this kind of system, they generate revenue from them.
Yeah. That was the question. Do you think that it could be a commercial?
Yes, of course.
Very soon?
I think so, because what is clear today that this system is very efficient. From a technical point of view, it's not a problem to integrate a 4G modem in a watch. The problem is the battery.
Battery.
So
I forgot to stop the recording.
Yeah.